Hello, and welcome to the Computing Conversations column. This column is from the June 2013 issue of IEEE Computer and is titled Gordon Bell, Building Blocks of Computing. There is supporting video material for this column that you can find in the IEEE Computer Society YouTube channel or in the IEEE Digital Library. I am the editor of the column, and I'm Charles Severance from the University of Michigan. Gordon Bell has had a long and varied career. An early employee of Digital Equipment Corporation, designer of many of DEC's PDP series of mini-computers, leader in computer science at the National Science Foundation, longtime proponent of the Computer History Museum in Mountain View, California, and the creator and funder of the Gordon Bell Prize, which annually the ACM awards for improvements to parallel and scalable computing. Today, he's a researcher emeritus at Microsoft. I recently met with Bell at the Computer History Museum in front of a fully restored and operational PDP-1. In the late 1950s, Bell was pursuing his PhD in speech recognition at MIT and working on analysis by synthesis.
I had built a tape control unit for this. What I needed was all these modules, flip-flops, AND gates, OR gates, all of the component things that are so low level to computer scientists. These are tiny areas of a piece of silicon. Those were the components, and so I went to Digital, who was selling components, to buy those, and so I bought 50 of them and put them together to make a tape control unit.
But once he moved on to building the software for speech recognition, he realized that all the fun was in the making and the building the hardware, and that achieving effective speech recognition with 1950s technology was virtually impossible.
What I learned from that was that basically I didn't want to be a researcher, that I really was an engineer, and certainly above all I didn't want to be a speech researcher, because I said, it was... I've experienced this with 2 or 3 speech researchers since that time. One of them was describing this as an ARPA contractor that he was going to conquer speech, and anybody who looks at speech and you say, my God, I can kind of recognize that, why I should be able to write a program. And so I basically said, okay, where do you want us to send the Nobel Prize when you do that? And it was just, and so I got out. I said it was going to take 20 years to do it.
DEC soon recruited Bell, and his first task was to design the PDP-1's input-output subsystem. As part of that design, he invented the first universal asynchronous receiver transmitter, or UART, which was essential for moving data between systems or components that didn't share a common clock. The focus on I/O meant that the PDP-1 became more of an extensible building block than a computer built for a particular purpose.
The first documentation I did about the PDP-1 was, I wrote a 32-page manual about how to connect stuff to the PDP-1, because we were enamored with how do you connect to that. And then the difference between the PDP-1 and then subsequent machines that we built were really the I/O got much more flexible, got easier to use, so that when somebody could read that manual, they'd say, oh my God, I'm going to connect that to a process control. I'm going to connect that and make it an oscilloscope. I'm going to make it a pulse height analyzer.
This approach, which focused on expandable building blocks and flexibility, led to the mini-computer. Its expandable architecture was a core idea for the PDP and VAC series of computers, and is what sets this category apart from supercomputers and mainframes.
What the mini-computer did, it enabled the computer to be used as a component in sort of everything, and that's where it was. And I just wrote an article about rise and fall of the mini-computer, and basically the editor, I went back and forth with the editors, but what happened was I had to say, look, the function that we were creating here there was nothing like it in the past. It wasn't a scaled down mainframe that you could interact with. That wasn't the goal that we had. It wasn't it wasn't a record keeper. It wasn't a computer in the sense of a supercomputer. We weren't after numbers, and we weren't after bits and keeping records. We were after a component that could be used in any number of ways, and it ended up being used to do message switching, to have telegraph lines come in and telegraph lines going out, which is the core part of networking today.
Much of the architecture in these mini-computers evolved from standardizing the connections and connectors, which led to bus architectures that allowed devices from vendors and system builders to be plugged into the same computer. DEC pioneered the original equipment manufacturer market with the PDP-8 that most of us consider to be the first mini-computer.
And the idea was to make these systems as flexible as possible, and so that they could be interconnected to. And
it's
so
a toy chest for engineers, basically.
So basically, the thing that's been the most, I'd say, I've had the most fun with is sort of thinking about buses and connecting things over my lifetime. So in this one, we had a core, processor memory and some I/O, and then wires radiated to connect to other things. And then we made the PDP-5, which was this, I'd say, the forerunner of the 8, was basically a single wire that ran out, and you attach things to that. And then when we made the PDP-11, we had a single wire for everything, and so all memories and processors and everything connected to that wire. And by that way, when we introduced Ethernet, because the first Ethernets was a single wire, and you connected computers to that wire. And I said at that time I said the Ethernet is the Unibus of the 80s.
With technologies like Unibus making it so that any enterprising engineer could prototype and build an expansion card, the number of applications for a mini-computer like the PDP-11 was limitless. DEC produced a standards-based expandable component, and almost 100 vendors, including Beckman Instruments, Foxborough, Western Electric, and Olivetti, used it for everything from process control to rocket navigation to telephony and telegraph operations. The PDP series of computers was a hacker's delight. It was where new innovations like the ARPANET could gestate. The notion of building a technology that's usable as a component has continued over time.
In every generation, you get a machine that is a computer that is a component. The microprocessor, as it was first came out, was a component. Once the microprocessor got a little bit bigger, the PC, that began to be used as a component. In fact, what we just talked about was this guy here, the cell phone, is now a component. This is the most amazing component you could ever get. We would never thought of that as a component, because what's in it is, I've got maybe 32, 64 gigabytes of secondary storage, so it'll store everything. It's got enormous processing power. It's got many radios in it, and it's got an accelerometer. It's got a GPS unit, and guess what? Who wants one of those? Well, all of these N-copter things, the geocopter, the 3-blade thing, the 4-blade, the 6-blade. Saw a 12-blade that carries people the other day. All of those things are controlled by this being the central part of that.
Video games are another example of a mini-computer-like architecture in which their central computing and storage capability is surrounded by rich sensors and other I/O forms. Examples of early computer video games abound, but the PDP-1 Space War is the first example of a widely available interactive game, because the early PDP systems were the first widely available mini-computers with a light pen and graphical display.
Harlan Anderson, one of the founders, I think, had discovered at the end of the year that he could give a computer away and get total tax deduction for that. And I I don't know that whether that was the thing that made us profitable that year or not, but in fact we gave, I don't know what number it was, but it's very early PDP-1 to MIT. And so right next door to the TX0, the transistorized computer, its ancestor, we put a PDP-1 in that next door room, and all of the students came in there. Steve Russell and Peter Sampson, Alan Kotok came in and took a lot of the software ideas that had been developed for PDP-1 and transformed them onto or that was on the TX0, put them on PDP-1, and that things like all of the first editor, which we called expensive typewriter, debugging, interactive debugging, all the light pen kinds of interactions, connections, and then I think the most famous one that is still in a sense in use was Space War.
While much of Bell's career has been dedicated to engineering and building state-of-the-art computing technology to be manufactured and sold, his most recent work has been to reflect on what we've seen and learned over the past 50 years of computing exploration. He describes his last 15 years as being an accidental researcher, exploring what it means to have your whole life captured digitally. He gets curious about an idea and then digs into it, connecting the past, present, and future in wonderfully interesting ways. If you'd like to see an example that describes the role of mini-computers in the history of computing, read Stars, The Rise and Fall of Mini-Computers. This column is from the June 2013 issue of IEEE Computer and is titled Gordon Bell, Building Blocks of Computing. There is supporting video material for this column that you can find in the IEEE Computer Society YouTube channel or in the IEEE Digital Library. I am the editor of the column, and I'm Charles Severance from the University of Michigan.